Yes. Yes, so I think it's time that we have our quiz break with me as an intermediate now. And my name is Sebastian Persson, and I'm a PhD student from Sweden. And I'm going to talk about PEtab.jl, which is basically a Julia package for setting up parameter estimation problems, basically defining the cost function. And just to get us all on the same page, I will start a bit with my background and what I mean with parameter estimation. So I am in the research field of systems biology, and in this field we typically build models of our biological systems in order to try to rationalize the data we are getting from experimentalists. And often these models can be translated to systems of ordinary differential equations. And when it comes to ODE modeling in systems biology, there are many challenges associated with them. And one of the main challenges is that typically the model parameters, you can see there on the left side, are unknown. So in order to see if our model can describe the biology at the hand, we need to estimate these parameters. And the way we typically do that is that we gather some experimental time-lapse data, as you see here. And then we typically have some start guess parameter value. We run some optimization, that is the parameter estimation, to try to find the parameters that best fits the data. And often the situation looks something like this. We do not really fit the data perfectly. So we need to iterate. We need to build new models to increase our understanding of the system. And often this model building is a very iterative process with many models. So therefore I would argue that one of the open challenges when it comes to parameter estimation is how we can fit the models to data as fast as possible. That is how we can fail as fast as possible, because you should never underestimate the importance of failing fast. Besides faster computations, other important challenges when it comes to parameter estimation is how you integrate different sources of data. Often we use quantitative data, but ideally we should be able to use qualitative data. And another open challenge is how we handle really large models that are realistic. This is currently outside the scope of most simulators, but maybe we can use surrogate modeling here. So what our goal was that we wanted to develop a software where we can kind of support all of these features that are worthwhile research directions. And as a starting point, we wanted to focus on achieving stable, fast, efficient parameter estimation. And a relevant question some of you in the audience might have is, why on earth do we want to have a package for setting up parameter estimation problems in Julia or setting up the cost function? Because the SciML ecosystem is, as Chris just talked about, pretty nice in this regard. You have a lot of flexibility. And the thing is that it's easy to set up your parameter estimation yourself if you have a simple case. So for example, if you have the time-lapse data I showed you in the previous slide, you can literally do this in 4 lines of code, and this is probably auto-differentiable, so all your problems are solved. But the thing is that in many real-life applications, things are a bit more complicated. So usually we have multiple observables. We are measuring data for different states of the ODEs at different times. We can code this ourselves, a bit more complicated. Usually we have different experimental conditions, which means that we are measuring data for different control parameters of the ODEs, so you need several forward simulations now. To make things funnier, people like to have the model at a steady state at time 0. Imagine you are giving a drug to a system. This system should probably be stationary at time 0. We can still code this ourselves, but you see, it's getting a bit more complicated. There are also some small dangers coding things yourself. For example, in the literature over the years, we have learned that it's often more efficient to estimate the parameters on the log scale. You can add this, but you need to be aware of this. Also, when you do parameter estimation, you typically want to have gradients. And if your model is small, you can probably use ForwardDiff in Julia, a forward mode, a very nice method. But if your model is large, you probably want to use some reverse approach like Zygote. And the people here probably know that getting your code to work with Zygote in a perfect manner out of the box, that can be a quest. So I think the take-home message here is that we can code our objective functions ourselves, but we might miss out on optimizations. And another questionable thing is if your code is reproducible. I would not want to send this to someone unless I dislike that person quite a lot. And it's questionable if it's correct. I mean, this code is not going to work, it has 3 bugs, but there might also be silent bugs. that are very hard to notice. And this is why we wanted to develop the package PEtab.jl, which brings me to the package itself. So PEtab.jl is a package for creating cost functions or objective functions in the Julia language. And we want to make it accessible to people who are working in Julia, but also those who are working outside, which means that when it comes to the models, we allow users to support, or rather provide, their dynamic model as a catalyst reaction system, an ODE system, or an SciML file. We also allow users to provide their parameter estimation information in a standard format, table format, or code it directly in Julia. And to make the entire modeling pipeline easier, we provide wrappers to the optimization package for fitting the model to data, but we also provide wrappers to Bayesian inference packages such as advanced HMC, which are the algorithms used in Turing. And as a software package, PEtab supports many things, but not everything. So what we have on the pipeline is also adding support for scientific machine learning, but also fitting stochastic models to data, which is a bit harder task. And as a package, PEtab has several benefits, and I would argue that one of the bigger ones is that we support different model formats. So everyone here might not be familiar with SciML. This is probably good for you because it's a very tough standard. But it's basically a standard format in systems biology, so it's a machine-readable language for models. The idea here is that you can create a model in SciML, submit it to a journal, and then other people can import this. It's reproducible. And SciML import is handled in PEtab via SciML importer, which is a package that was born out of PEtab. And how it works is that it basically imports your models into catalyst reaction systems, which allows for many things, such as stochastic simulations or deterministic simulations. It's also a very thoroughly tested software. So it currently passes around 1,270 cases of the around 800 test cases in the SciML test suite. So this basically means it supports most of the SciML features. What we are not supporting, that we are not passing, are like delayed differential equations or events with delay. But if you really want these features, just submit an issue, and I unfortunately have to implement it. And when it comes to the syntax of SciML importer, we try to make it as easy as possible. So the package only exports a single function, load SciML. So you only need to provide your model file. Then it will give you a past reaction network callback set with model events, which then can easily be simulated, for example, as a stochastic differential equation or as an ordinary differential equation. Besides supporting a standard format in your model, we also support a standard format when it comes to your parameter estimation problem. So the name PEtab, which I actually don't remember what it stands for, is a standard format in the systems biology for formulating parameter estimation problems. So basically, what you need to do here is that you need to provide a model, an SciML file, and tables that contain all the information you need to do parameter estimation, such as measurements, observables, the standard information. And once you do it, it's very easy for us to pass the problem. You just need to provide a YAML path, which basically binds the PEtab files together into a PEtab model, and then the PEtab model can become a PEtab ODE problem with good default choices. Then you can create an optimization problem, and you can just fit your model to data. And I mean, I strongly encourage people to use standard formats because this makes things more reproducible. But we also recognize that maybe not everybody wants to work with, SciML files. So we also allow people to set up the parameter estimation problems themselves in Julia. And here, we allow the model, your dynamic model, to be provided as a catalyst reaction system or as a modeling toolkit ODE system. And I know this is the old syntax for modeling toolkit. We are in the process of updating to version 9, but we are waiting on Catalyst, which is our core dependency. Besides providing your dynamic model, you also need to provide other minimal information. So you need to provide which your observables are, which you do via PEtab observable. And here you can basically provide it as an algebraic formula. So we have that this op_sum is basically that you're observing your enzyme E and your substrate enzyme complex. You can make it as nasty as you want here, and then you just provide your measurement formula. You also need to provide which parameters to estimate, because typically you don't want to estimate all the parameters in your dynamic model. This is done via PEtab parameter, where you can also put a prior if you want to do maximum a posteriori estimates. Then you just need to read your measurement data as a data frame, and you can bundle all of this together into a PEtab model. You can create a PEtab ODE problem, and you're done. So overall, we try to make it packaged as accessible as possible when it comes to setting up the problem. Another benefit I actually consider to be quite a good benefit with the package is that it works with likelihoods, so you're working within a good statistical foundation. So this means that when you are fitting your model to data, the cost function that is generated by PEtab is a likelihood function, so you're going to do a maximum likelihood estimation. Besides actually being statistically robust in this sense, you're also going to have other benefits, like you can do identifiability analysis to assess uncertainty in your parameters, model selection using likelihood-based tools like AIC or BIC, and sensitivity analysis. But also, if you're doing Bayesian inference, and if you provide priors, we can do Bayesian inference with algorithms such as those in adaptive MCMC, advanced HMC used by Turing, and also pigeons, which are all something we provide wrappers for. So besides setting up the problem and doing the modeling pipeline, we also have some fun things on the inside of the PEtab package. And one is that we probably spend too much time thinking about gradients. So if your model is small, we support gradient computations via the ForwardDiff package. And this is often the most efficient approach for models with less than 75 parameters. And we also done some internal hacks that makes it possible for the package to be faster than naively taking ForwardDiff from your objective function. We also recognize that sometimes model can be large, then we need to use adjoint approaches. So we also wrap the adjoint sensitivity functionality in the SciMLSensitivity package. If you don't care about these things, we have gradient methods for small and big models. Also, we integrate with the rest of the SciML ecosystem. So we have access to ODE solvers for both small and big problems. And to see why this is a benefit, we can take a look at this plot here. So what you're seeing here is the runtime for 29 benchmark models sorted based on size. And this is the CVOD BDF solver. It's quite famous for being the workhorse in a lot of established software like Amici, Lee-Broner, D2D, industry standard. Here you're seeing the runtime for the RODAS 5P solver. It's a Rosenbach solver specialized for smaller models. And you can see that, at least for the smaller models, it has quite a good advantage. And if we look at the accuracy here, we can also see it's actually more accurate if you use the same tolerances. So I think this kind of nicely highlights why we want to have these kind of toolboxes in Julia, because then we can also choose an ODE solver that is specialized to a problem we are actually working with. Lastly, as a benefit with the package, is that I also would like to argue that it's a fast package in the spirit of Julia. And I always think that, standing in front of an audience, presenting, saying that you have a fast software without any additional evidence is a bit too bold of a statement. And something fun we could actually do in this project is that we could do quite a thorough benchmark. Because the thing is that PEtab, it basically imports a standard format. So this means that we can also compare against other tools, non-Julia tools, that also import standards formats. In particular, we could do a very thorough benchmark against PyPesto, which uses Amici as a simulation engine. And here I want to highlight that Amici is a very efficient C++ wrapper to the Sundial CVOD library. It does a lot of fun things like model preprocessing via SymPy. So in short, it's fast, it's been thoroughly tested. I think it's a worthwhile thing to compare against it. Also, we can make sure that our benchmark is relevant. So in this study, we only decided to benchmark against real models with real data from the PEtab benchmark collection. So we're going to have all the fun things with, for example, model misspecification. And the first thing we wanted to benchmark using this approach was gradient computation runtimes. Because the thing is that when you do parameter estimation, just as in machine learning, you want to have the gradients. And computing the gradient is substantially more expensive than computing your objective function. So this is actually your computational bottleneck. So what you're seeing in this plot is the runtime for the BERM benchmark model with two different Julia ODE solvers against Amici, two different colors. And hopefully you can see, if the screen is big enough, that for the BERM model, PEtab is approximately twice as fast when computing the gradient via the ForwardDiff package. Naturally, we looked at more than one model, and in general, we saw for 14 out of 90 models that we benchmarked, the PEtab was often between 2 to 3 times as fast when it came to computing the gradient. So basically, this highlights that using ForwardDiff compared to the traditional forward sensitivity approach seems to be more computationally scalable. Another benefit with using automatic differentiation is that we can also compute the second-order derivative, the Hessian. And here we can look at the scaling behavior by looking at the runtime ratio between your objective function and the Hessian. And we typically saw in our benchmarks that this ratio is smaller than the number of parameters squared. This is quite good scaling behavior because this algorithm is quadratic in its complexity. And having access to the Hessian when fitting models to the data can also be very beneficial. And to see why, we can take a look at this plot. And here you are seeing what we like to call a waterfall plot. So when we are fitting models to data in systems biology, we use a pretty naive approach. We have 1,000 start guesses, and then for each one of those, we run parameter estimation. Then we record the final objective value. And you want as many runs as possible to reach that valley in the end, because that often indicates that we found the global optima. The results you're seeing here are from using PyPesto with feeders, which is a Newton trust region method that would be awesome to have in Julia, but it's from Python, with a Gauss-Newton Hessian approximation. Here you see the same results when we use feeders with the full Hessian. You see that more runs converge to the global optima. And we can also see that we get even better results if we use the interior point Newton method from the opt-in package. Some people might argue in this case that maybe we don't need a full Hessian because we still have sufficiently good performance. However, for some models, it can actually make quite considerable difference, as we can see here for the Fujita benchmark model. So what I primed you on here is basically parameter estimation results for 2 models. But naturally, in our benchmark study, we wanted to evaluate more than 2 models. And when it comes to evaluating parameter estimation performance between 2 softwares, this is a bit of a tricky task. But the way we decided to do this is that we used PEtab and we used Amici with the same optimizer, the feeders trust region method. So we're using the same optimizer, but different simulation engines. And again, we can see for the BERM benchmark model that we were approximately twice as fast. And this is something that held in general, that for 15, or rather 16 actually, better than I expected, 16 out of 19 models, we were often between 2 to 4 times as fast when doing the parameter estimation. And I would argue that there's actually only 2 models where we are really outperformed. But runtime is not everything when you are fitting models to data. It's also important that you have good convergence properties. And one way you can measure this is by looking at the runtime per converged run, and then you can normalize this score across models. And if you do that, you achieve something that looks like this. So the way you read this plot is that you look per column, and here the brightest yellow dot corresponds to the setting that performed the best. And then you look, or per row probably, row column, yes. And then when you look across the columns, you see across models. The short story here is that for 15 out of 19 models, PEtab.jl achieved the best score. For 2 models, it's very hard to draw any general conclusion because very few runs actually converged at all. For 2 models, we are totally outperformed, which is also, area for improvement. But in general, I think this quite nicely highlights that as a Julia package, even compared to other state-of-the-art packages in systems biology, PEtab.jl achieves good performance when it comes to fitting models to data. And naturally, I would always be more happy to talk more about this package, but in the interest of time, I think it's time that we move on to the conclusions. So basically, in this talk, I presented 2 Julia packages, PEtab.jl and SciML importer. They both work within an ecosystem that is based on setting up cost functions for fitting models that are driven by differential equations to data. And my research field is systems biology, but I mean, this is a general thing. As long as you have a model that is driven by a differential equation and you want to fit it, this is where it works. And typically, when we decided to do a realistic benchmark against other state-of-the-art tools, we saw that PEtab as a package achieved state-of-the-art performance, at least for models with less than 100 parameters, which are the ones we thoroughly benchmarked. However, when it comes to developing software, you're never really done, so I think there are some relevant improvement areas going forward. And what we want to add is that we want to add more utility functions to make it more user-friendly. Probably after the workshop yesterday, I also need to update the documentation. We also want to add a Bayesian inference benchmark. So we are currently benchmarking different Bayesian inference ways to doing inference of the posterior. And if anyone works here with, for example, Turing or something, I would be happy to discuss different algorithms in the context of ODEs. What I would like to have in the package, however, which is also a bit outside of my scope at the moment, but would be very nice to have, is more efficient ways of computing the Hessian. Because currently in PEtab, we are computing the Hessian with a forward over forward approach. This is quadratic complexity. We did some benchmarks recently where we were horribly outperformed by Diffrax, which is a YAX-based differential equation solver, because they can do a reverse over forward, or forward over reverse approach. Moreover, where I think it's, at least for us, a large area of improvement is doing adjoint sensitivity analysis. Because here we are also outperformed by Diffrax, so I think this is also an area where we could improve even further. Both packages are also available on GitHub. You can download them as normal Julia packages. If they are useful in your research, please give them a star. It would help me, especially when writing postdoc grants. The benchmarks I presented today are hopefully soon published in a paper. Last year on JuliaCon, this paper went under review. Next year on JuliaCon, I hope I can say that the paper is no longer under review. But we shall see. Review number 3 is a bit slow. And naturally, the work I've done here could not have been possible to do alone. So I just want to acknowledge Fabian, Stefan, and Jan for helping setting up the benchmark that we did. For the package development, I want to highlight Rafael, but also especially Torkel Luhmann, who helped a lot with the Catalyst integration with the package. Also Swedish Lab, which is kind of the research group I am part of, and SFF, which are kind of the funding agency that gives me money to do this. So with this, I think we are on time, which means that we can move on to any questions. I choose.
Yeah, thanks. I was wondering if this always works, or if there are certain characteristics of or your solver or your equations that that the optimization becomes difficult.
I mean, if your optimization problem is very, very hard, like you have an oscillatory model, it's questionable if we are going to be able to fit the model to data in a satisfactory way. But as long as your model is a differential equation and you put up in the PEtab framework, at least we should be able to compute the objective function and your gradient. So you can always set up the problem, but then depending on how easy it is to fit the model to the data, we can't guarantee that you're going to be able to fit it without maybe using specialized methods. But for setting up the problem, we have wide support.
Okay, but no guidelines or already first.
We have guidelines in the documentation for which settings we recommend for certain problem characteristics, which optimizer we recommend. And once this paper finally gets published, we will have even more guidelines.
Okay, thank you.
Yes.
Yeah, two main questions. So first question is, what's the reason why you're not using the forward over reverse Hessian? Because that's existed in SciMLSensitivity since like 2019.
I didn't get it to work, and I spent too much time on trying to get it to work.
Okay, we should talk about that in soon then. The other thing is, what's the reason for not using similar least squares optimization methods, right? Because you're comparing a BFGS method, which is a general nonlinear optimization method, to a nonlinear least squares method, right? The Gauss-Newton approach. The Gauss-Newton approach can actually make a few optimizations. So the fact that you're faster means that you're still doing more work and you're still being faster than them is actually that's quite nice. But I mean, what's the reason for not using, say, trust region Gauss-Newton from nonlinear solve.jl rather than using the BFGS approach?
Actually, I think you got that bit a bit slightly incorrect. So we are actually using just the Gauss-Newton as an Hessian approximation, so we're not working within a least square framework within any software, either PyPesto or PEtab. But the reason why we didn't use the trust region method from nonlinear solve is because we are working with bounded constrained box constraints. And at least when we started to do these benchmarks, Optim was the relevant package, and the trust region method in Optim doesn't work with box constraints. And I don't know if the trust region method in nonlinear solve at the moment works with box constraints. If it does that, we would be very happy because we are looking for that kind of algorithm. Because what we have seen generally is that we need to have the constraints, bounds, because otherwise integration failures.
Yeah. So that works through a transformation approach. Well, we could talk more on that one as well.
Yes. Yes.
Okay, I think I might have missed this part, but when you were showing the models, you were when you were defining the models earlier, you used catalyst and a symbolic model with the differential equation.jl. Does this also work for the old notation for differential equation for differential equations that were in symbolic models?
No. So we want to have the modeling a symbolic representation, either catalyst or as an ODE system, because that makes it much easier for us to bookkeep all the model parameters.
Okay.
Because if you code it like input vector p, then you know which p is which.
All right.
Maybe you then.
Very short. Do you support constraints between the parameters?
Aha, you mean one parameter is less than a...
Yes, or one parameter is 2 times another, or equal, or similar.
No, but we should, and it shouldn't be that hard to do it, so I would always be happy to discuss that, because we also have the optimizers that should be able to handle that. Yeah. So I think we're done.